In the previous video, I left you with this odd notion that the antiderivative of a function really includes this constant c, which could be any number. It could be any number that's not a variable. Those of you who are very literal-minded might be a little bit disturbed by this. It's like you might say, well, how can that possibly be an answer if this constant c could be any number that's not a variable? It could be a 1, or it could be 102, or it could be 42. And I will tell you, in physics, we'll either use this antiderivative in such a way that c will cancel out, or you will be given in the physics problem enough information so that c can be absolutely determined. So in physics, this constant c is generally something that we can find out. A lot of times it's 0, and it helps us, gives us a little bit of leeway for setting the solutions for any physics problem that matches up to reality. And sadly, in math, calculus teachers take great joy in taking off points for failing to remember that the antiderivative does, in fact, include this plus c, because it's true, remember what the antiderivative is, the derivative of this has to equal that. And in fact, that's all of integral calculus is basically, the integral calculus is full of these problems where here's an equation and you have to guess an equation such that when I take the derivative of this, it gives you this. And actually that might seem easy, but there's in fact about 16 different ways to help you guess what this equation is. And that's what integral calculus, that's what makes it hard. Fortunately, in AP Physics, there's only about 6 different possible equations that you could have for this f of x. And if you haven't already gotten the list of the 6 integrals that you need to know for AP Physics, you're going to get the list next time. One of the ways we'll get around the indeterminate nature of the plus c in the antiderivative in physics is that almost always in physics we'll want to know the area underneath a graph between 2 specific limits, say on the x-axis x equals a and x equals b. It's because in physics, when we take the integral, it's often we'll want to know the work done by a force as an object moves from position A to position B. And so the beginning of the integral is definitely known, and the ending of the integral area is definitely known because the object only moves from here to here. We'll only want to know the work done from there to there. So in a physics problem, there's always very specific limits as to what exact area we want to find out. And for instance, that would be this whole area in this odd-shaped, I don't know, trapezoid with a curvy top. I guess it's not a trapezoid if it doesn't have a straight edge there. But this odd-shaped area here, we would like to know exactly what the area of that function is, because perhaps if this function is the force on an object and this is the actual work done between when the force moved the object from position A to position B. So when we know the starting point of the area and the ending point for the area, we call that a definite integral, and I suppose that's because we definitely know the beginning and end points of the area in question. And here's how we write it. And we'll say the integral from a to b of f of x. Usually a is going to be a number, like here it might be 3, and b will be another number, so here it might be 7. So these are generally 2 x values, and f of x is whatever the function is. So in this case, our integral might look like the integral from 3 to 7 of x squared dx. And so what this is asking is, on the function x squared, what is the area between x equals 3 and x equals 7, for instance? And that's how you would write that specifically. And so the physics problem would be how much work is done when the object moves from a position of x equals 3 meters to a position of x equals 7 meters. If this were the equation for force. The equation for force was x squared, for instance. So that could be a physics problem. And notice in physics problem, it's generally a specific position where an object's, we want to start tracking an object's movement, and a specific endpoint. And so those things are sort of definite, and this notation, or this type of integral, is called a definite integral. There's a standard procedure for dealing with definite integrals, and I believe it's called vertical bar notation, and it goes like this. If you get an integral like this, what you do is you write down the antiderivative, whatever that equation is, f of x plus c, and we don't know what this unknown constant c is, but we do have this idea that this must be the area somehow of this graph. And then you're going to write a vertical bar, and the vertical bar has a on the bottom and b on top, which corresponds to the beginning of the area and the ending of the area. And this is pretty much just to remind you that what you're going to do is you're going to plug in b into this equation and find out some equation for this entire area from 0 to b, and plus some unknown value c. And then what you're going to do, you're going to plug in a into this equation, and what that'll do is it'll tell you the entire area from 0 to a, this little piece, plus some unknown value c. And then you're going to subtract those two areas, and that will leave you the desired area of that you want to find between a and b. So notice that the area, this area here, if we take this whole area from 0 to b and subtract off the area from 0 to a, we'll have this middle area right here. And so what vertical bar notation means, we plug in the value b into our area equation here, and we plug in the value a into our area equation here, and we subtract them. And so what that is doing, it is finding this whole area plus some unknown constant c, and this whole area plus some unknown constant c that we don't know, and we're going to subtract them. And what will remain is this area in between, and that's the area that we want to find in a definite integral. Now the amazing thing and the wonderful thing about calculus is this is an unknown constant, whatever it is, but when we do this subtraction, this is an unknown constant, but whatever the unknown constant is, it's the same unknown constant here as it is here. So we are guaranteed that this constant will be canceled when we distribute the minus sign and subtract. So with definite integrals, even though the antiderivative always does have this plus c, and it could be any constant value, and we don't know what it is, when we have a definite integral, whatever value it is, we are guaranteed that it's going to cancel out. So a definite integral actually looks just like this, with no c in it at all. So that's a really clever way of avoiding the fact that we don't know what this value c is. Let me make some room. Oh, it's hard to make room. Hold on. So let me make some room for this. And I feel like this is quite a clever, like using these definite integrals, and in fact, in physics, we're always going to have, or a lot of the times in our problems, we'll have definite integrals, and here's what it looks like if we have an actual equation. Here's how we would write this problem if we had integral of x squared dx, and that was a force equation that we're trying to find the amount of work done from position 3 meters to position 7 meters. Then we would write equals, and the antiderivative of x squared is x cubed over 3, and then we'll write vertical bar notation from 3 to 7. And here notice I could put in c, but since I know that it's going to cancel out, I think I don't have to put in c, and I won't get counted off for in a math class. You for sure won't get counted off for not including c in this position in a physics class. And this vertical bar notation is to remind you, oh, I'm not done yet. So I found the antiderivative of x squared, and I can check myself. The derivative of x cubed is 3x squared, and the 3 out in front cancels with this, giving me just x squared. So I know that is the antiderivative, and the vertical bar notation is to remind me that I still have to plug in 7 cubed for x, and then I have to plug in 3 cubed in for x, just like this. I plug in, and then I have to subtract them. And if this were my equation, the actual area between these two, if this were 3 and this were 7, the actual area would be 114.3 minus 9, or 105.3. So notice I could have written plus c here, and that means I would have a plus c here, but then I'd have a minus plus c here, and the c's would cancel out. So for definite integrals, we totally, if we have a specific endpoint to our integral and a specific beginning point to our integral, the plus c factor in the antiderivative will always cancel out, and you can actually get a real actual value for your definite integral. And in this case, this would be the work done in joules of a force if the force was x squared, if the force was proportional to x squared, and an object moves from x equals 3 meters to x equals 7 meters. 105.3 joules of work would have been done on that force. So it does have an actual meaning in physics. And notice when we actually get a value, the plus c part that is sort of indefinite about the integral totally cancels out. The other way of getting around the unknown nature of c is called a boundary value problem. In this type of problem, you're actually given certain parameters on the problem, its boundaries, or extra information that will help you exactly determine what c is, what actual value c is. And for instance, this is the classic application in physics, and you might remember that in chapter 2, when we looked at x of t, the slope of the position versus time graph is velocity. So if you're given a position versus time graph, you take its derivative to get its velocity. And the slope of a velocity versus time graph is acceleration. So what I've drawn is graphs for constant acceleration. That's how come I have a horizontal line here. Now, remember I told you that physics and calculus were twin children of Isaac Newton. They were both invented at the same time, and one was for the other, and I think it was calculus was for physics. And here's one of the reasons why, that because the derivative, the slope of position versus time is velocity, and the derivative of velocity versus time graph is acceleration, it only makes sense that the antiderivative of acceleration must be the velocity versus time graph, and the antiderivative of velocity versus time must be the position versus time graph. Isn't that, to me, that's just a wonderful thing that calculus will do that, and how the interaction between calculus and physics is so beautiful. So here's how this problem will go. What you're expected to know for integral calculus now are these facts about acceleration versus time graph and velocity versus time graph. Namely, the equation for velocity versus time is the integral of the equation for acceleration versus time, just like the acceleration is the derivative of the velocity. Since the integral is the antiderivative, the converse must also be true. Actually, I'm not sure if that's a converse or if it's the opposite. But anyway, the velocity versus time is the integral of acceleration versus time. And that also means the position versus time equation is the integral of the velocity versus time equation, just like this was the derivative of this, the velocity versus time graph is the slope of the position versus time graph. The position versus time graph is the integral of the velocity versus time graph. But interestingly enough, it's also the area of the velocity versus time graph. Also, the velocity versus time graph is the area of the acceleration versus time graph. Now, in order to actually do these sorts of problems using the integral, you must have some added information or the boundary values, or else you just can't determine c. So in this type of problem, we must have additional pieces of information in order to solve the problem. So let's say that we're given the equation a of t equals some constant value, letter a. So a is a constant, so that would be like 3 meters per second squared. But I'm going to leave it as letter a, and for a reason that you'll see in a second. In order to fully solve this problem, we need a boundary value, or some additional piece of information that'll help us determine c. In this case, our boundary value is going to be the velocity at time equals 0. And we're going to say the velocity at time equals 0 is v naught. And remember, v naught was our standard initial velocity in our chapter 2 problems. V naught stood for the velocity at time equals 0. So that's going to be, this part is our boundary value. So that's an extra piece of information beyond telling me what the equation for acceleration is. They must additionally tell me some other piece of information about the velocity before I can fully solve the problem. So what I do is I'm going to write this known equality, which is true for physics, just as the fact that the velocity is the derivative of position and acceleration is the derivative of velocity. The same is true that velocity is the integral of acceleration. So I just write this out with my given acceleration. I'm going to make some more room here. So I know that the velocity is the integral of the acceleration versus time equation, or in this case, the integral of a dt, where a is some constant, and dt, remember, dt is just our integral notation. It's saying I'm going to be having an infinite sum of rectangles with width dt, whose height is always height a, and that's my velocity. That's my integral of the acceleration versus time, and I know that that's going to equal velocity. Just like when you're taking a derivative, if you have a constant out in front of an equation, you can factor that constant to the outside of the derivative part. The same thing works for integrals. And so we'll get this curious thing, the constant a times the integral of dt. Whenever you have just the integral of dt, you should think about it in this way. So this constant a integral dt, notice that there's not actually a variable here. I'm expecting like a variable here. And how you should think of this is as the integral of 1 dt. Because after all, 1 times dt is the same as dt. But the good thing about 1 dt is you can also write it like this. 1 dt can be written as t to the 0 power, because any number to the 0 power is 1. Alright, and if I know that t to the 0 power, and 1 is really t to the 0 power, then I can apply my integral pattern, where I just take t to the 0 power plus 1, and then divide up by 1, and so I can see that the integral of t to the 0 power is t to the first power plus c. Now there's another funny little thing about calculus that I need to make some room for, so I'm going to actually make even more room over here. So I'm going to move all these things. So the funny thing about calculus is that they're such mathematicians. I think it was probably Leibniz was such a joker with his notation. So what we have here is v of t is equal to the constant a times t to the 1 power 1 plus c, also known as a times t plus c. Now if you distribute the a, you get at plus ac. And here's the funny part. What we always do in calculus is this a times c, well, c can be any constant, and even though it's times a, c can be any constant, so we'll just write that as at plus c, where this c is different from this c. In fact, this c here is this c times a. But since c could be any number times a could also be any number c. Isn't that kind of funny? That's some sort of subtle joke in integral calculus, and we do this all the time. Anytime you get the letter c times any other constant, we always substitute as, oh, that's a different letter c, but we still write it as letter c. It doesn't matter. It really doesn't matter. Since c could be any number, it's still any number, only this time it's any number times our constant acceleration a. So what we really have for our velocity versus time equation is the velocity versus time equation equals at plus c, where c is an unknown constant. But remember in the beginning of the problem I told you, well, we have a boundary condition, and the boundary condition was v at time equals 0 was supposed to be called v naught. So what we do is we plug in 0 for time, and in this case we put 0 here, and we're told that when we plug in 0 for time, the equation should equal v naught. So what we get when we plug in 0, a times 0 is going to be 0, and so our equation when we plug in v of t equals 0 is just equal to c, but that has to be equal to v naught. So in fact our boundary condition in fact told us that c equals v naught. And this is what you always do for boundary conditions. If you get v of 0 equals v naught, as soon as you get your equation for v, it's going to have some unknown constant c in. What you do is you plug in 0 into the equation and set that equation equal to whatever they tell you it's equal to, and that will allow you to solve for c. And in fact, we know now that c equals v naught, and the only way we know that is because we had this initial condition, this boundary value. And so our equation is in fact putting the c at, rearranging the c. v of t equals v naught plus at, which, as you might recall, is the exact same equation for v on page 21 of the physics book for the special case of constant acceleration. I want to continue my example, and hopefully we'll get the right equation for x of t that's on page 21. But I want to point out a few features of how integrals are a lot like derivatives. So our equation of v of t is going to be v naught plus at. And notice that, just like derivatives, if you have two things plus each other and you're taking the integral of them, that's the same thing as the integral of each thing separately. So you can distribute the integral sign, and you can also distribute the dt. So if you have an equation, a function that's two functions plus each other, the integral of those two is the integral of one function plus the integral of the other function. Now, here's another case where I have a constant times dt, and here's a case where I have a constant in front of a variable, and in both cases the constants, just like in derivatives, the constants will factor outside of the integral sign, and it'll look like that. And I'd like you to remember that integral of just dt, you should really think of that as t to the 0 power, and actually we kind of know how to do this integral by now. And here I need to make some room. So all of these are going to be like this. So this is t to the 0 power, and so what that's going to look like is t to the 0 plus 1 over 0 plus 1 inside this integral. That's what this integral is. And it's still got this constant out in front that I'm going to distribute through, and I'm going to remember that v naught times c is still c. And then for this integral, I have t to the 1 power, so I have the integral of that is 1 plus 1 divided by 1 plus 1, also plus c, and I'm going to distribute this a times t to the t squared over 2 is what it's going to be, plus a times c, but I'm also going to call that c. So let me make a little bit more room here. And so this all equals, let me just move that up. So if I simplify a little bit, I get these two, and I'm still going to distribute my v naught, I'm still going to distribute my a, and make a little more room. And then I distribute v naught through the parentheses, and I distribute a through the parentheses, and notice this half gives me the familiar 1/2 at squared, and over here I have a v naught. But I have these two v naught c, an ac term that are curious, and integral calculus does something truly funny with these. In integral calculus, we group the v naught c and the ac together, and then we call everything in the parentheses c, because remember, c can be any number, and v naught c plus ac is still any constant c, and we also call that c. Is that funny? I think that's just funny. So we have for our equation of x of t equals v naught t plus 1/2 at squared plus c. And in order to figure out what c is, we need some initial conditions, like for instance, at time equals 0, the position is x naught. So if we're given this extra information, this initial condition, or maybe it's a boundary value condition, what we're going to do is we're going to plug in 0 for t and set x of t all equal to x naught. So plugging in 0 here and 0 here and setting it equal to x naught gives us 0 plus c equals x naught, and so that tells us that c in fact does equal x naught. And so we can put x naught in for c in our original equation, which gives us finally this familiar expression, where x of t minus x naught equals v naught t plus 1/2 at squared. Now x of t, remember, is the position at time t, also known as x final, or just regular x on the page 21 equations. So x of t is just regular x, and this is exactly the same equation that integral calculus tells you, provided you have these initial conditions. If you know the position at time t equals 0, which, remember, in chapter 2 we always said, well, that's x naught, that's what the naught stands for, t equals 0. All right, so you can see where physics comes from calculus, or is it that calculus comes from physics? I'm really not sure, but in either case, they're both really cool.